Hello there and welcome to this update video on the Star Wars Battlefront engine reimplementation project. This will be a rather technical video, so I'll not only show you in-game footage of the current state of the art, but also somewhat go into the depth of development itself, so be warned. But first, I'll provide a summary of what this project is actually about and what has been done so far to everyone who is new to this project. If you're already familiar with the project, you might want to skip ahead by either clicking on one of the following time sections or using the timestamps provided in the video description. So let's dive in. What is this project about? You may be familiar with other reimplementation projects like OpenDiablo or OpenAge. These projects implement complete clones of the original game engines by first reverse engineering them, then re-implement them using modern libraries and build pipelines, port them to modern machines and operating systems, fixing known bugs and sometimes even add new features. Instead of doing a re-implementation like that from scratch, this project is not so much about reverse engineering the original binary and implement an exact clone of it, but more of implementing a custom clone that mirrors the behavior of the original game engine. We can do this because the original game has a nice separation between engine code and game code. Most of the game code is actually written in Lua, with the compiled Lua binaries being embedded into the game's asset files, as are all of the object definitions for unit classes like Clone Trooper or vehicles like the ATTE, whereas the actual base class behavior is implemented in the engine. So the game data interacts with the engine either through the Lua API, like set the max and current health of this generator object to 150, or object definitions like here's a clone engineer unit which should behave like a soldier and has this much health and can run that fast, or other conventions. This is also the part that's moddable through the mod tools, whereas the engine part isn't. Of course, the engine is also responsible for all the basic necessary stuff like providing a rendering architecture, animation system, user input handling, physics, a sound engine and more. Since our goal here is to provide a substitute for the engine part, we need to provide all these features while still matching the original interface as best as possible. By utilizing the Unity game engine, we can immediately cancel out most of this list, since it's already provided for us, and focus ourselves on the important part of interfacing with the game. Animation system turned out to be an exception here, but more on that later. Also better put a question mark on networking, since Unity's new networking API is still in development to this day. One feature we are explicitly not using for original assets is the Unity asset database, since we want to load everything from the original game files directly at runtime. Ripping copyrighted material from the original game like 3D meshes, textures, etc. and shipping them alongside the binary is something we don't want to do for obvious reasons. So, what's needed to be implemented for all of that to happen? Well, first of all, we needed to get our hands on the original game data in a way we can read it at runtime. For that, we needed to read the original game files, which most of the time come in a proprietary binary format named with the file extension .lvl. These files follow a strict hierarchically tree structure with nested chunks of various data. We put the code for reading these files into a separate library and then call that library from Unity code. Now that we had access to all the data, we needed to convert it at runtime into data Unity understands and instantiate game objects, meshes, textures, etc. from it, which led us to our first successful map import. As I said, most of the game code is written in Lua, with the .lvl files not actually containing any Lua source code, but just compiled virtual machine instructions. In order to execute these in our environment, we needed a functioning Lua 5.0 virtual machine running in 64-bit, which is capable of executing 32-bit instructions, since downgrading the entire project to 32-bit was not even considered an option. Additionally, the developers of the original Battlefront slightly deviated from the 5.0 standard and modified the stack sizes and data types of the virtual machine. So we forked from the Lua 5.0 source and altered the virtual machine code accordingly. Having the Lua virtual machine set up and running, we needed to implement the actual API exposed to the game code. As you can see, most of these API methods are still doing nothing, and some of them will probably never do anything, since their purpose becomes obsolete with this reimplementation. What's implemented though is the bare minimum to get the map script to execute, most notably do file, read data file, set property and such. Next up was a reflection system that made it possible to define base classes and their properties, which are then referenced by the object definitions of the game files and made their properties accessible through Lua. From here on, we started to implement base classes like command post, soldier and cannon, and after putting some rudimentary UI on top of everything, we finally got to the point where stuff started working. So far, everything showed in the last video ran within the Unity editor only, and I wanted to build the project in order to see where it breaks. And it broke immediately. Not while building, that actually went fine without errors, but when running the resulting binary. As you can see here, we've got nothing but T-posing characters, and as I said before, Unity's animation system turned out to be the problem. Before addressing the main issue here, let me quickly explain how animation was handled until that point. Like you would expect, Unity has a nice little animation system in place for animation state management, state transition blending, blend trees, layering and masking of bones, etc. Since we are not importing any animations through the asset database, but loading them at runtime, we cannot exactly know beforehand what animations are going to be assigned to each state. Unity provides API methods for cases like this, such that you're able to replace any animation in any state. So just assigning some empty animation to all states in the editor and then replacing them at runtime worked fine. What's not possible though is creating avatar masks at runtime, which is necessary if you want to use multiple layers in your animation controller. But this is not the only problem. The main reason why our characters are T-posing here in the final build, but not in the editor, is that the setCurve method of animation clip only works at runtime for legacy animation clips. And without that method working, we simply got no animation data at all. This was the last nail in the coffin for using Unity's animation system. To be fair, 99.99% of games developed out there wouldn't even want to use such a feature at all, except maybe if you want to develop the next Spore or something. Since we can't use Unity's animation system, we need to implement our own. So what needs to be done exactly? Luckily, we don't need to implement mesh skinning, meaning we don't need to manipulate all the vertices according to their bone assignments. That's something Unity's skinned mesh renderer component still does for us. What we need to manipulate though are all the bones themselves. Animating a skinned mesh just means memorizing the location and rotation of each bone over time. To do that, we need to implement keyframes, animation curves and clips from scratch. Not only that, we also need a sufficient substitute for state handling, transitioning and blending. Since implementing such a system can be generalized, I put all the code into a separate GitHub repository and integrated that into this project. Maybe someone runs into a similar problem in Unity and needs a solution like this. Also, you want to implement such a feature in a multi-threaded, data-oriented way. Just as an example, the regular humanoid skeleton in OG Battlefront has 22 bones. Targeting a humanoid instance count of let's say 1024 humanoids with an update rate of 60 frames per second, in worst case, we already need to set the transforms of 1,351,680 bone game objects per second. We can use Unity's burst compiler and job system for that matter, and after most of the fundamental implementation has been done, we can see our first animation result playing a single animation. Next up was state handling, masking and transition blending. Here we see two animations playing at once, with each of them being masked to specific bones of the upper and lower body respectively. For transition blending, since the old Battlefront was using a fairly simple animation system, we can probably get away with just doing linear interpolation. Here you can see a comparison of transitioning the upper body between the reloading animation and the run forward animation, with and without transition blending. If you take a closer look, you can see how on the left side the animation is switching instantly, while on the right side it's blending smoothly. This problem gets a little bit more complex when dealing with lower body transitioning. Right now everything is linear interpolation only, but maybe this will be extended to be a better dynamic time warp implementation, depending on how severe any fragments are that may appear in the future. If you're interested in this topic, I put links to some papers in the video description. Having all of these animation features ready to use, we can finally think about implementing a character controller for humanoids. The controller is not nearly finished, but I'll show you what's been done so far. So what we've got here are all the different states from standing over shooting to falling, landing and turning, with all the crouch states still missing at this point, and the logic of which state should be active depending on the controller and world input. Additionally, we want individual control over some bones overriding the animation depending on the controller input. Here you can see how the head is always looking at the view direction when idling and looking around without aiming. When aiming, the whole torso will move towards the view direction. For turning left and right, we used the provided turning animations and an arbitrarily chosen threshold after how many degrees the turning should trigger. Landing animations are triggered similarly. The duration of falling determines which landing animation will be played and how long you are prohibited to move with it. So far, we've only seen one character instance at a time. But how about more instances? Let's start with 64 instances, which is the maximum in the original Battlefront, at least in vanilla with no Uber mode activated. The characters are controlled by a simple script and are made immovable for demonstration purposes. Runs nice and smooth without lowering the level of detail here. Let's quadruple that to 256. Again to 1024. Now let's do some aiming practice. Nice. Other parts that are involved with animations are doors and vehicles. Doors were pretty trivial, just playing the provided animation either forward or backwards, depending on the boolean proximity of at least one soldier in a given radius. Hovering vehicles on the other hand were a bit trickier. In fact, they share the same base class with vehicles on wheels, using so-called spring bodies defined within object definitions. We used the definitions of these spring bodies to do simple raycasts downwards of the respective locations, applying an upwards force depending on the distance and the spring settings respectively. For vehicles on wheels, wheel sections are working as well. In OG Battlefront, hover vehicle animations are described in a single animation containing exactly 9 frames, which are then interpolated two-dimensionally, depending on the pilot's controller input respectively. Here you can see the first iteration of the hover-based class in action on a TX fighter tank. As you can see, you can enter vehicles and drive around with correct interpolation of the different animation poses, depending on the pilot's input. What's implemented as well are sections and aimers. These are used to define spots on the vehicle a soldier can occupy, as well as the equipped weapon for each spot, if any. One major advantage of a reimplementation like in this case is that custom mod maps are supported as well, since they interact with the engine in the same way just like the vanilla game files do. But before you cheer, one key difference here is that many modern mod maps out there squeeze out the last bit of available interface the original engine provides. Since our implementation is not at all complete at this point, with the main priority being to be compatible with the vanilla game files first, this in turn means mod map support will only grow slowly over time and may even never be fully finished in all regards. Just to demonstrate that mod maps work in principle, let me quickly load some mod map here. Some other new feature you've already seen by now is the minimap, displaying all the command posts. As you can see, right now the minimap texture is way off from where it should be, but at least command posts are selectable and you can spawn on them. What's also working is the conquest mode in general. Enough Lua API has been implemented for this mode to be fully functional. Let me quickly demonstrate this by going to each command post and capture it. All command posts are captured and the victory timer is counting down as expected. Our Lua environment is running just fine. Besides custom maps, another advantage is that the build result of this project is really tiny in size, compared to the overall game files. As of now, it's just about 82 MB in total, 28 MB zipped, and an installation will require no more than just extracting the zip to your Battlefront installation directory or the like. At this point, there probably won't be any zip provided for you to download though, since it doesn't really make sense to ship any builds during development when stuff is either broken or not working as intended. Go check the project's repository for releases. If there is no release yet and you're nevertheless interested in trying to test it out for yourself, you'll need to clone and build the entire project for yourself. Instructions on how to do so will follow on the repository's README and our Discord. That's it so far. The video actually turned out to be way longer than expected and some stuff actually had to be cut. All I got left to say is thank you for watching, like and share this video and consider joining our Discord if you're interested in the project. This project is currently developed by 2 enthusiasts, Nihilisk and myself, and we both drowned a lot of working hours into this. You can find the links to the Discord server, the project's main GitHub repository and all related repositories in the video description.